Next up is section 4.5, and 4.5 takes us away from just evaluating sine and cosine, and now we're going to actually look at the graphs of sine and cosine. So let's go ahead, and I'm just going to write down some equations. We're going to look at the function f of x equals sine of x. We're also going to look at the function g of x equals cosine of x. Now, before we begin, I want to just point out here that x is an angle, and our outputs, so y in this case, is a ratio or a point on the unit circle, however you like to think about it. And so these are different from our x and y values that we were using when we did unit circle stuff. Just something to keep in mind that x and y are sort of different now. X is taking the place of theta, and y is taking the place of those x and y values we find on the unit circle. Okay. So let's go ahead first of all and just create a table of values. So we're going to go ahead and do a table for sine to begin with. And I'm going to start at 0. And we'll be doing this in degrees. So if you take a look at sine, you'll notice that sine of 0 degrees is 0. Good start. Sine of 0 degrees is 0. And then let's go ahead and pick a couple other points on our unit circle. So I started here at 0. I'm going to go up to 45, and then we'll hit 90. So we'll just kind of go around this unit circle like this. And then we'll head back to our original. So let's go with 45 degrees. Now sine of 45, if you remember, this is sine of pi over 4. This is root 2 over 2. This is approximately equal to 0.7. So we'll use 0.7 in this case, just because it's easier to graph numbers than square roots. 90 degrees is going to give me 1, and then next we'll have 135, which will also be 0.7. And then we're going to have 180 degrees, a half rotation, which will be 0. 225, continuing around the unit circle, will give me negative 0.7. 270 is negative 1. 315, and then a full rotation. I'm back at 0. Now we could keep going, right? So I could keep adding 45 and keep going around the circle. But notice that it'll just keep repeating this pattern. So if I get to 405, this angle and this one are actually coterminal. So that means that my sine is actually going to be the same. It's just going to be 0.7. So this is going to repeat. So let's go ahead and graph sine. I'm going to have x-axis and y-axis. Remember, x is my angle, and y is a ratio. And so the maximum my y value ever gets to is 1. The minimum is negative 1. Let's start here at 0, 0. We'll go up to about 360, but I'll probably go a little bit beyond that. Now what I like to do is break this up into 4 components, basically the different axes on the unit circle. So I'm going to break 360 into half, and then I'm going to break 180 into half. And then also we technically have, this isn't halfway, it's at about 0.7. And so what the graph ends up doing is the following. It kind of goes up, curving up, and then curving back down again, and then it's going to get down here to 270, negative 1, and then it's going to go back to 360. And then like I was saying, we could keep going, so after 360 I'll end up at 450, and so my graph would end up going up to, oops. Try to draw this a little bit more to scale. I know it's not going to be perfect. So this would be 450. And so then it's going to come back around again. Additionally, we could look at negative angles, so I could do negative 45 degrees, and that's going to be coterminal with 315. And so that would be kind of going back this way. I'd end up with a graph like this. And this point over here would be negative 180. Because negative 180 is coterminal with 180. And then this point over here that we're hitting would be 540 degrees. And that would continue. You could just keep adding 360 if you wanted. And then for cosine, it's going to be a really similar process. I'm going to have x, and I'm going to have g of x for cosine. Let's just go with kind of the big ones, 0, 90, 180, 270, 360. At 0, cosine is 1. At 90, cosine is 0. At 180, it's negative 1. 270 is 0. And then 360 is 1. And then the pattern will repeat. So we'll start over here at 0. We'll go up here to about 360, and then I'll break that in half. And so then my graph will just kind of be like sine, except I'm starting up there, and then I'm dropping down like this. So again, curving, it's not straight lines. They actually kind of look like parabolas, but they're not. But this would be cosine. So we've graphed y equals cosine of x. We've also graphed y equals sine of x. Now this is all fine and dandy, this is good, but usually what you're going to want to do is actually graph these in radians. So let's go ahead and switch everything into our mindset of radians. Oh, by the way, this was x again, and then this was y. So let's switch everything to radians. And then these are going to be our actual sort of complete graphs. You can think of these as the parent functions. So first I'm going to graph sine of x. We have x, we have y. I'm going to go from 1 to negative 1, and let's go out to, so 2 pi is 360, and I'll go actually a little bit further out. So we'll have 2 pi, we'll have pi. On the other side, I'll do negative 2 pi and negative pi, and then let's just go up to 3 pi as well. So what I'm doing here, rather than going up by 1, 2, 3, I'm going up by a pi. Now I can choose whatever I want on my axis. Just keep in mind pi is about 3.14. So really this would be like 1, 2, 3, and 2 pi is about 6.28. So we go 4, 5, 6. So notice that those numbers don't go away. I'm just writing everything in terms of pi because it makes it a little bit easier. And I'm setting up the exact same way I did before, where I had 360 and 90 and 180, because pi is actually 180 degrees. But now I'm sort of graphing in more, I guess, real numbers rather than degrees. Okay, let's break this up a little bit further. So I have pi over 2 here, and then I have 3 pi over 2. This will be negative pi over 2. This one will be negative 3 pi over 2. Okay, so for sine, we start here at 0, 0. We need to get up to 1, and we come back down again. And this process continues. Going back the other way, we're going to end up down here. Notice I'm getting all these points because I remember that these are sort of the axes, right? So pi over 2 is on the unit circle on the y-axis. And so sine is either 1 or negative 1 or 0. And then pi, we're over here. And so that's how I'm getting these numbers. Okay, back to it. Go ahead and finish this graph off. And this would be my graph. And then I can put arrows just to show that that pattern continues. It keeps going up and down forever. So this should be locked into your notes somewhere, easily accessible. This is the parent function for all graphs we look at with sine of x. Next, let's do cosine. Okay, so with cosine, same sort of deal. We'll go to pi, pi, pi over 2, 3 pi over 2. Let's go up to 3 pi. I don't really care about what's in between them. And then we'll go to negative 2 pi, negative pi. Oops, I forgot my 1 and negative 1, and then this is my y-axis, and this is my x. Okay, so cosine starts up there, comes down, and then keeps repeating that pattern. So it's going to sort of go like this. Then on this side, it's going to curve around here. And then it'll curve back. So there's my graph of cosine. Okay. Now, a couple points to make about this. First of all, these graphs are used to model periodic behavior. Because they go on forever, we could actually use this to model any sort of phenomena that reoccurs in nature. So for example, one of the ones I always think about is the tides. So at the beach, the tide comes in and then it goes out, and really it follows the lunar cycle. And so the lunar cycle is what we would call periodic, and it actually follows, or can be, sine and cosine can be used to model the moon's behavior. Another one is, if you're in physics and you've ever dealt with spring mechanics, you'll probably have seen some problems involving sine and cosine, because when you're holding a weight on a spring, it goes up and down and it oscillates and eventually dies off. And there's other ones as well. Electromagnetic waves we use to model, or we use trig functions to model. So there's lots of different examples of why we might want to use this. Now, a couple of keywords that I need to define here. The first one is the amplitude. So we'll talk about the amplitude. We're going to talk about the period. Another word for period, and this is probably pretty common if you've been in physics, is the wavelength. We'll also talk about the midline, and sometimes you'll hear me say average value. And then finally, we'll talk about a phase shift. Okay, so the amplitude of a graph, of a trig graph, is basically its height. From its midline. Or you can think about it as its depth, I guess, or just distance from the midline. But basically when I'm talking about the amplitude, I haven't actually defined midline, but if you're looking at this graph, you'll notice this is sort of the middle. So this would be the midline, or the average value, y equals 0 in this case. The amplitude is this distance here. And in this case, that distance is amplitude. Oh boy. Sorry, I was right at the limit of my notes there, my notes app, so that's why I wasn't writing. So this is the amplitude. And in this case, it equals 1. So for the parent function, the amplitude is 1. The midline is y equals 0. The midline is the, it's the midline, right? So it's the line that goes through the middle of the graph's maximum and minimum points. And so then for our parent function, the amplitude is 1, and the midline is the line y equals 0. Okay, now the period or the wavelength is the measure from one point to its repeating point, or basically coterminal angles apart. So in this graph here, let's go up to sine and do this with sine. If I start right here, I would go up, I come back down, come back around again, and I end up here. The distance it took me to do that was 2 pi. Alternatively, let's say we're looking at cosine. Let's say I start up here, I come down, and then I head back up again. And so once again, this distance is 2 pi. So it's basically the distance it takes before repeating itself. The distance traveled by the graph before repeating itself. And once again, for the parent functions, the period is 2 pi. So everything you see in red here and circled is for the parent function. And then the phase shift just means, did we move left or right? So sometimes you don't necessarily want to start a sine function at 0. You don't want to start a cosine function at 1. Sometimes you want to shift it away. And that's called the phase shift. So we'll come back to phase shift more in some of the examples we see. So this is just moving right or left. And in this case, oops, I'll just call this C, and we're going to say C equals 0. Okay. And last thing for this video is I just want to mention the domain and the range. So the domain for both cosine and sine is all real numbers because they can go on forever and ever. The range for both of them, they're stuck between -1 and 1. They can't be anything else. Great, and so that concludes our intro video, and the next ones we'll start solving some actual problems with sine and cosine.